Hi, my name is Nidhi and I'll be talking to you today about the extraction of cellulose fibers for sanitary napkins. Cellulose as a source of fiber. Cellulose comes from plant fibers, which are mainly composed of cellulose, hemicellulose, and lignin. Cellulose is the main product of natural occurring fibers like cotton, flax, hemp, etc. Cellulose is a main component of sanitary napkins in modern biotechnological processing. The main characteristic is that cellulose is a linear polymer, which makes it ideal for sanitary napkins. It increases the absorbency and does not change its structural properties. The extraction of cellulose fiber from sisal plants occurs in 6 main steps. 1. Obtain the plant from South America. 2. Treatment of the sisal plant through various chemicals. 3. Preconditioning of the fiber and the drying of it. 4. Chopping up of fibers. 5. Dewaxing. And 6. Extraction of the fiber. So 1. Why do we use sisal plants? Sisal plants are abundantly found in South America, and they do have high cellulose content, which makes it beneficial for the usage of sanitary napkins. So, second point, the treatment of a sisal plant. So, the main reagents that are used are toluene, ethanol, sodium hydroxide, sodium borate, hydrogen peroxide and hydrogen hydroxide, nitric acid, acetic acid, and sodium bicarbonate. So, preconditioning drying is the third step of this process. The preconditioning of the fibers is done by washing fibers thoroughly using the distilled water. The main purpose of distilled water is that it washes away most of the impurities that are present within the fiber. The main advantage of using distilled water is that it does not compromise the chemical or structural properties of the various fibers that will be extracted from sisal fibers, which is vital for sanitary napkins. Once fibers have been conditioned, it is then subjected to 80 degrees for 24 hours so that it is able to dry out and ensure that the sterilization process is complete. Chopping of fibers is the fourth process. The fibers are chopped to specific lengths of 5 to 10 millimeters long. The sizing is important for the fibers as it ensures that the uptake of all chemicals is relatively evenly distributed amongst all fibers. 5. Dewaxing. So a ratio of 2 to 1 toluene and ethanol mixture is boiled. The main properties of ethanol and toluene is that it acts as a solvent which is a relatively higher density, which does not change the key properties of the fiber. The apparatus that is used to be able to perform this is called the Socklet extractor. How does the Socklet extractor work? This use of this apparatus is the final and most important part of extracting fibers from the sisal plant. Socklet extractors are used to be able to extract lipids from solid or semi-solid materials. The main material of the Socklet extractor are the condenser, the extraction chamber, the thimble, the siphon arm, the extraction solvent towards the bottom, which is normally ethanol, boiling flask, and the vapor outlet, which is towards the top. Okay, how does it work? So the sisal fibers are inserted inside the thimble. The thimble is made from material which allows an easy flow of liquid from the solid to be able to pass through. The organic solvent, which is most likely ethanol in this case, is added to the flask at the bottom and heated to commence the extraction process. The Socklet acts as a reflex medium, where the boiling of organic solvents rises up towards the condenser and gets condensed and trickles back down into the thimble. This action repeats itself until all the contents has been extracted from the solid. When the fibers are collected from the Socklet, further filtration is performed and is washed by pure ethanol for 30 minutes until it is dried. Extraction of cellulose fiber from the sisal fibers. There are main steps for the extraction of cellulose fiber from sisal fibers. Fibers are pre-treated with 0.1 mol of sodium hydroxide at a volume of 50% ethanol for 3 hours at 45 degrees. After the whole 3 hours has elapsed, hydrogen peroxide is then added as a pH buffer at 45 degrees. They are added at percentage intervals of 0.5, 1.0, 2.0, and 3.0 respectively. The fibers are then treated with 10% sodium hydroxide, sodium tetraborate, dehydrate, i.e. borax, and water at a constant temperature of 28 degrees for 15 hours. Nitric acid is then added for 15 minutes, being subjected to a temperature of 120 degrees. Once it is cooled, the fibers are then washed with 95% ethanol. Once that is done, the cellulose is now extracted from the ethanol mixture and is set to dry in the oven at 60 degrees until a constant weight is achieved. This whole process has been done with constant agitation by using impellers at the bottom throughout the entire extraction procedure to ensure that there is an equal distribution of all chemicals. Now the cellulose fiber is formed. However, once the extraction process is complete, various methods of screening must be used to be able to differentiate between commercially ready cellulose and lignin, which is formed as a byproduct of cellulose in many of these procedures. There are several types of screening that the fibers go through. 1. Thermogravimetric analysis, TGA. 2. Differential scanning calorimetry measurements, DSC. 3. Fourier transform infrared spectroscopy, FTIS. And scanning electron microscopy examination, SEM. So the thermogravimetric analysis, it measures the mass of the substance, which gets monitored as a function of temperature and time. The cellulose samples are projected to a controlled temperature in controlled environments. This analysis is able to characterize a vast range of fibers based on the temperature changes. Differential scanning calorimetry, or the DSC, is a thermal analysis technique. This looks at the material's heat capacity. The cellulose is heated in these two chambers over here. It is then cooled and heated while being subjected to extreme temperatures through these. It is then tracked by this computer as the heat flow fluctuates. The main advantage of this measurement is that you can see the difference in glass transition. Glass transition is a material changes from solid state, shifting to a rubbery, flexible material. This instrument is very accurate, which helps to detect the purity of the cellulose samples through the heat capacity. The Fourier transform infrared spectroscopy, or the FTIS, shows a highly specific fingerprints of microorganisms which allow accurate identification at the species and subspecies level. The main advantage of this spectroscopy is that it is non-destructive as well as non-invasive. These two characteristics enable the biomass to be examined to completion. Now, the scanning electron microscopy examination, or SEM, takes X-ray-like photographs of fibers and microfiber surfaces. It achieves the image by focusing the electron beam over here across the surface of the fiber, which is the specimen. Then it is reflected, or it gets detected or backscattered by electron signals, which is the secondary electron detector in this image here. This then is extrapolated into a graph once the results are combined, and it provides identification of the type of fiber that has been used on the stage. Now, the type of fiber is able to be, you can analyze the type of fiber being used by the quantitative comparison of cellulose fibers. Now that the production and the scanning process of cellulose fibers has been completed, now the upstream process, or the production of sanitary napkins for the wider market, is continued. Now we'll be going through the basic structure of sanitary pads. Now, sanitary pads, as you know, are used by females to be able to absorb lots of things. The top sheet consists of polyethylene or polypropylene fabric, creating the two main layers between the pad. The absorbent layer is where the cellulose fiber sits. Recall that cellulose fiber has a massive advantage of it being very highly absorbent and tough, which basically makes it the perfect material to be able to be inserted into the middle of the sanitary pad. Materials with direct or indirect skin contact has relationship to why the cellulose fiber is in between the two layers. The top sheet continually contacts the skin, although its material hardly transfers during its use due to its tough, non-irritable properties. The indirect skin contact is where most of the absorbent part of the napkin sits, which is cellulose. Due to the use of the napkin, these constituents have been tested to avoid reflux situations, and the cellulose has shown that less than 5% of times that it occurs. Now, the regulations for sanitary products in Australia is quite stringent. The main rule is that is constantly being applied year to year by the Therapeutic Goods Act, or the TGA, is that all sanitary products should be manufactured using materials involving cellulose, textile polymers, or a combination of both. This is due to its absorbent properties. They also have very specific requirements in relation to the packaging, especially the disposing of these products, as it can pose an environmental threat. That was my presentation on extraction of cellulose fibers. These are my references that I've used, and I hope you enjoyed, and I wish you luck for everything else. Thank you.